In this lesson, we will derive a very important tool for a large portion of numerical analysis. Now, before you mentally check out, let me encourage you that this derivation is quite quick and simple if you have taken a bit of calculus. First, we assume that a function f of x can be represented by a polynomial with an infinite number of terms. Here I have truncated the series to the fourth order and used an ellipsis to represent continuation. As of now, my coefficients, represented by subscripted a's, are unknown. Now the clever part is to evaluate this polynomial at x equals 0. Notice that each term except the first one is equal to 0. Therefore, a sub 0 is equal to f of 0. Continuing onward, we take the first derivative of both the left-hand side and right-hand side. Remember that the derivative of a polynomial can be found quite simply by employing the power rule. Similar to before, we can evaluate both sides at x equals 0 and solve for the coefficient a sub 1. This pattern continues with the second derivative, third derivative, and as many terms as you care to include. So in effect, we can solve for the value of many unknown coefficients simply by taking another derivative, which is a simple process for polynomials, and solving one by one. Plugging our solved coefficients back into the original form of our polynomial, we can see something like this. In a textbook, you might see it labeled as a Maclaurin polynomial. As a quick reminder, the exclamation point after a number is called the factorial symbol. The factorial pattern results from taking repeated derivatives of a polynomial using the power rule. The Taylor polynomial is very similar to the Maclaurin polynomial, except it is centered about a instead of 0. We say that the Taylor polynomial is a more general representation. The Maclaurin polynomial is technically a specific case of the Taylor polynomial for which a is equal to 0, but we don't need to split hairs about that. Now let's take a look at an example. Our function is sine x. Sine 0 is equal to 0. The first derivative is cosine x, and cosine 0 is equal to 1. Notice that by the fourth derivative, the pattern has come full circle and will repeat itself. In the right column, notice that each even derivative is equal to 0, and then the odd derivatives alternate between positive and negative 1. Writing the terms as one polynomial with our solved coefficients, sine x can be represented like this. I leave this as an exercise to you, but in a similar fashion, cosine x can be represented like this. These expressions should look familiar from our previous studies in trigonometry. There they were merely introduced and used for computation, but now we should have a little better understanding where they come from. Also note that these representations shed light on why sine x is sometimes called an odd function, and cosine x an even function. In another lesson, we will employ the Taylor polynomial to develop a powerful technique. Stay tuned for that, and as always, thank you for watching. If you enjoyed this video, please consider sharing it with a friend. I greatly appreciate your support.